Welcome back to part 2 of our Three.js tutorial series, where we continue our journey of creating realistic planets on the browser. In our previous tutorial, we covered the basics of setting up a simple scene and rendered a sphere on the screen. This time we are going to build on those basics and dive deeper into geometries and materials. For this tutorial, we'll be using some additional resources, specifically a set of images that include a world map, add normal map, add specular map, add night lights, Saturn, Saturn's rings, moon normal map, and star field. I'll be explaining their use as we go along, and you can find them on GitHub. Let's also go ahead and import them and get that out of the way. And these imports simply hold the location of the resource. Before we dive into geometry, let's quickly review the coordinate system used in Three.js. Three.js uses a right-hand coordinate system, which means that if you hold out your right hand like this, your index finger points in the positive X direction, your middle finger in the positive Y direction, and your thumb points in the positive Z direction. All objects in our scene will by default be positioned at the origin, meaning that the origin is the point about which an object rotates or scales, unless you decide to translate the object elsewhere, like we did with the camera. Now let's talk about geometry. And in the context of 3D graphics, geometry refers to the shape of the object. This shape is defined using a collection of points called vertices, each of which can have various attributes such as its position in 3D space, color, UV coordinates, and surface normals. These attributes are stored in typed arrays for efficient memory usage and fast access. To illustrate how to create and use these attributes, let's create a simple triangle. Let's start with position to get the flow. The position attribute represents the vertex's location in 3D space and is typically represented by 3 values per vertex. These values are stored consecutively in the float32 array. Each group of 3 numbers in the array corresponds to the X, Y, and Z coordinates of a single vertex in 3D space. In this case, we have defined 3 vertices. To store these attributes, we'll be using a class called a buffer attribute, which is a way of organizing data in a format that can be easily processed by the graphics card. When creating a buffer attribute object for the position attributes, an item size of 3 is specified, indicating that each vertex has 3 values, which are the X, Y, and Z coordinates. We then create our geometry using the buffer geometry class and set position data like so. If you wanted to paint the triangle with solid color, you would follow the same procedure. First, create a float32 array for the color data. The color attribute represents the vertex's color in red, green, and blue channels, and is represented by 3 values per vertex. And just like position, these values are stored consecutively in a float32 array. Each group of 3 numbers in the color array corresponds to the red, green, and blue values of a single color. In this case, we have defined 3 colors, red, green, and blue. And again, we'll be using the buffer attribute object to store color information. An item size of 3 is specified when creating a buffer attribute object for the color attributes. Let's also go ahead and add the color to our geometry. The third attribute that we need to talk about is the surface normals. Surface normal attributes represent the direction that the surface is facing at a particular vertex and have 3 values per vertex. Each group of 3 numbers in the normals array corresponds to the X, Y, and Z components of a single surface normal vector. In this case, we have defined 3 surface normals, all pointing in the positive Z direction. Let's create a buffer attribute for it like so, and then add it to our geometry. We also have UV attributes, which are used to map a 2D image onto a 3D object and have 2 values per vertex, representing the vertex's position in the 2D texture map. This is so that faces know where within an image to extract image data. The U value corresponds to the horizontal position in the texture map, while the V value corresponds to the vertical position. The data might look something like this, in which case the triangle would be textured using this portion of the image. And just like we've done before, we create a buffer attribute object for it like so, with the exception that the item size is 2 instead of 3, since we have 2 values per vertex. And we finally add it to geometry object. Once we've defined the attribute arrays in our geometry, we can use them to create faces. Faces can be defined using an index buffer, which is an array of indices where each group of 3 indices corresponds to a single face. Each number in the indices array corresponds to the index of the vertex in the attributes array. In this case, the indices 0, 1, and 2 specify the first, second, and third vertices in the positions array respectively, which make up the first face. We can then set the indices in our geometry like so. If we now use this geometry to create an object, it would look like this on the browser. Nice! More complex meshes like spheres extend this concept by positioning vertices in 3D space to form the desired shape. For example, to create a sphere, vertices are arranged in a spherical pattern. These vertices are then used to form triangular faces, and surface normals are calculated to determine how light interacts with the faces. This process creates the illusion of a three-dimensional object. With that understanding of geometry, let's discuss materials in Three.js. The materials are essentially small programs called shaders that run on the GPU and use geometry data to paint 3D objects on the screen. Three.js offers many options for materials depending on your needs. Let me give you a quick rundown of some of the commonly used materials available to you and their purposes. The simplest material in Three.js is Mesh Basic Material. It does not react to light and is used in cases where the object does not need to interact with light. So this is how a sphere would look like if you used Mesh Basic Material on it. Then you have Mesh Lambert Material. This one is affected by light, but it does not have specular highlights. It's a good choice for matte surfaces such as wood, paper, fabric, and so on that are not reflective. Mesh Foam Material is similar to Mesh Lambert Material, but it adds specular highlights, making it suitable for shiny surfaces. Mesh Standard Material is a physically based material, meaning it is geared more towards creating realistic renderings, which it achieves by incorporating properties like roughness and metalness. Mesh Physical Material is an extension of Mesh Standard Material. It is more computationally expensive than some of the other materials, but it offers a high level of realism and control over the appearance of objects. It's a great choice when you need to create complex, realistic materials in your 3D scene. And then we have Shader Material, which is a more advanced material that allows you to define your own custom shaders for unique effects. We shall be creating this material in the next video. Let's go ahead and use Mesh Basic Material to create a star field. To do this, create a large sphere that encompasses the camera, so we are viewing it from inside. We already set the camera's Z position to 10, and the sphere is going to be centered at the origin by default, so the radius needs to be something greater than 10 for us to be inside the sphere. Let's make it 30. Three.js materials take an object as an argument in their constructor, which you can use to set various properties for how you want the material to look. So for example, if you want to use a uniform color, you can use the color property and assign a color to it. Setting the color this way is an alternative to using the color attribute array in geometry, especially if you know the color will be uniform. If you want to use vertex colors, set the vertex colors property to 3.vertexColors. Another option is to supply an image to be mapped onto the object using the map property. This is exactly what we want. Create a new instance of texture loader, set the location of the image, ensure that the side property of the material is set to double side, allowing us to see the material from inside the sphere. To save on computation, double side is not enabled by default, as in many cases you only need to see one side of an object, such as the outside of a sphere. You might want to move the camera around for different perspectives. You can do this by simply importing orbit controls, then create an instance of the class, supplying the camera and the canvas as constructor arguments. And now you can drag the mouse, holding down the left mouse button to orbit, use the right mouse button to pan, and scroll to zoom. Most geometries are going to have the appropriate image mappings, but there are cases where you need to modify how the image is mapped. Let's create the planet Saturn to demonstrate a potential issue that you might run into. Creating a sphere is straightforward. You just need to use a new sphere geometry. This time we'll use mesh physical material, but you can also use a cheaper material like mesh foam material, which will work just fine. We'll texture the sphere using the map property in this image, resulting in this. The rings are where problems begin. Ring geometry is an appropriate choice for the rings. The first argument is the inner radius, the second is the outer radius, and the third is a beta segment, which represents the number of radius segments. This number should be large enough to ensure that the rings look more like a circle than a polygon. The last argument we need to supply is 5 segments, which is the number of circumferential segments. We only need 1 in this case. We can use this image as our texture, and the idea is that it will be stretched out along the ring. Let's give it a try. Nope. The image is mapped differently than expected. Luckily, we don't need to create a whole new geometry. We can modify the UV mappings to achieve the desired results, but first we need to understand the default UV mappings. The image is being stretched out into a square and a donut shape cut from it. However, we want the UV coordinates on the ring to correspond to a warped rectangle. The vertices for ring geometry are constructed using trigonometry, starting with the inner vertices and then the outer. Let's create 2 variables representing the UVs for the inner and outer rings. We'll also create a for loop with the iterations from 0 to segment count, calculating the UVs for the inner and outer vertices. Keep in mind, UVs have 2 components. U depends on how far along the image we are horizontally, and V is just 0 or 1 depending on whether it's the inner or the outer ring. Let's create a new buffer attribute array and spread the UV arrays into it. Finally, we update the UVs in our geometry. Now you should have the correct mappings. You might have noticed that the rings and the planet are not properly aligned. The rings are currently along the longitudes, but we want them to slice through the equator and tilt the whole thing slightly. Otherwise, we won't be able to see the rings, as ring geometry does not have depth. We can apply a rotation to the rings by setting the x rotation to math.pi divided by 2, which corresponds to a 90-degree rotation on the x-axis. Then we need to parent the rings to the sphere by adding the rings to the sphere instead of the scene. This is so that rotating the sphere also rotates the rings. We can then apply a slight rotation to the sphere along the x-axis as well. Something like 0.1 radians should do, and this is what you end up with. Moving on, let's now discuss the moon. As you might have guessed, it's another sphere with a texture for the surface. To make the craters more pronounced, we use another image called a normal map. A normal map is used to enhance the details on the surface of an object. For example, I have this normal map, which I'll assign to the normal map property of our material, similar to how we assign the map property. And this is the new look of the moon with the normal map. Comparing the images side by side, with and without a normal map, you can see the difference. And that's all I did for the moon. The process is similar for the Earth with a few additions. We create a sphere and texture it with an image, a world map in this case, and add a normal map to increase realism. We also have another type of image called a specular map, which tells the material which parts of the object are more reflective. For the Earth, water regions are more reflective than land. To use an image for the specular map, set the specular map property of the material the same way that you would a map or a normal map. And water surfaces should now be more reflective than land. For the clouds, we create an even larger sphere with cloud texture and making sure to enable transparency. As for the atmosphere, it's another sphere that is larger still. This time we use a solid blue color with low opacity. And now it looks like this in the browser. In the previous video, we discussed how to create animations by updating the property we want to animate inside the animation loop function, since this function is called recursively. Let's go ahead and simulate Earth's rotation by updating the rotation along the y-axis of both clouds and Earth spheres. And it's looking good. This is the basic method of creating the Earth. We are limited by what the default materials can do. In the next video, we shall make this scene even more realistic with our own custom shader material and then wrap things up with creating the sun. This is Francis, wishing you happy coding, and I'll see you in the next one.